Hi everyone. In this class, we are going to see limit concepts in differential calculus and its related problems. So first we see limit of a function. Suppose we are asked to sketch the graph of the function f of x, which is given by f of x is equivalent to x cube minus 1 by x minus 1 if x not is equivalent to 1. For all values other than x is equal to 1, we can use standard curve sketching techniques. However, at x is equal to 1, it is not clear what to expect because here we observe this problem. F of x is equal to x cube minus 1 by x minus 1. If we put x is equal to 1, what will happen? X is equal to 1 cube minus 1 divided by 1 minus 1. That is, we can get 0 by 0, which is indeterminate form. So it is not clear what to expect at x is equal to 1. So for this, we can consider this table. So x is equivalent to, we can write x is equal to 0 0.75, 0.9, 0.99 and 0.999, 1 and 1.001, 1.01, 1.1, 1.25. And by using this function, so we can get f of x values. And we observe this at x is equal to 0.999. What about the value? 2.997. And x is equal to 1.001. What about 3.003? That is, it's a neighborhood of the point x is equivalent to 1. So we consider this 2.997, which is equivalent to 3, and 3.003, that is also equivalent to 3. So that is, f of x approaches 3 from the left hand side, and also f of x approaches to 3 from the right hand side. So simplify the function f of x. So what you get? This is nothing but a cube minus b cube. We can use the formula a minus b into a square plus ab plus b square. So using that formula, we can get x minus 1 into x square plus x plus 1 divided by x minus 1. So x minus 1 cancel. So we cancel this two. We can get x square plus x plus 1. So the graph of f of x is the graph of the parabola y is equal to x square plus x plus 1 with a hole at 1, 3. Because at 1 the function is not defined, but approximately the value is equivalent to 3. So x cannot equal to 1, so we can move arbitrarily close to 1, and as a result f of x moves arbitrarily close to 3. At x is equal to 1, we have a hole. That is, the function is not defined at x is equal to 1, even though from the left hand side, if we approach or we approach from the right hand side, the value f of x value should be 3. So we can write by using limit notation, limit extend to 1 f of x is equivalent to 3. So here we cannot write f of value at x is equivalent to 3. So we can write limit x tending to 1 f of x is equivalent to 3. So now we see one-sided limit. Already we discussed what is left hand and right hand limits. So the left hand limit is the limit of f of x as x approaches to the value a from the left, and is denoted by limit extend to a minus f of x. So a minus, we can use this notation, a superscript minus. Similarly, the right hand limit is the limit of f of x as x approaches to the value a from the right hand, and is denoted by limit extend to a plus f of x. That is, when you draw like this, here this is a. So x approaches to a from the left. Similarly, x approaches to a from the right. So for a given function y is equal to f of x, if left hand limit is equivalent to right hand limit, and it is equivalent to a finite value, say L, then we can say that limit exists at x is equal to a, and we can write limit extend to a f of x is equivalent to L. Suppose any one of the limit does not exist, then we can say limit does not exist at that point. Now we see limit laws. Suppose that c is a constant and the limit extend to a f of x and the limit extend to a g of x exist. Then limit extend to a f of x plus or minus g of x, sum or difference of two functions. We can write limit extend to a f of x plus or minus limit extend to a g of x. That is, we can operate that limit inside. And the limit extend to a c into f of x is equivalent to that c we can take outside. So c into limit extend to a f of x. Similarly for product, if you have product of two functions f of x and g of x, limit extend to a f of x into g of x, we can write which is equivalent to limit extend to a f of x into limit extend to a g of x. And by quotient, limit extend to a f of x by g of x is equivalent to limit extend to a f of x divided by limit extend to a g of x, provided the denominator is not is equivalent to 0. Now we see some examples. First problem, evaluate limit extend to 3 x minus 1 by x square plus 2x minus 3. Solution. So take the given function limit extend to 3 and the given function. Now we put x is equivalent to 3. So x is equivalent to 3 minus 1 divided by 3 square plus 2 into 3 minus 3. So 3 minus 1 is nothing but 2. The denominator, if we simplify, we can get 12, and 2 we can common term we can cancel, we can get 1 by 6. Second problem, evaluate limit extend to minus 2 x cube plus 2x square minus 1 divided by 5 minus 3x. Solution, limit extend to minus 2 x cube plus 2x square minus 1 divided by 5 minus 3x. So now we put x is equal to minus 2. So minus 2 whole cube plus 2 into minus 2 square minus 1 divided by 5 minus 3 into minus 2. So we simplify minus 2 whole cube is nothing but minus 8, and here minus 2 whole square is nothing but plus 4. 4 into 2 8 minus 1 divided by 5 minus into minus plus, so 3 into 2 6. So after simplifying this, we can get minus 1 by 11. Third problem, evaluate limit extend to 2 x square minus 3x plus 2 divided by x minus 2. So in this problem, if you apply limit extend to 2 directly, what will happen? So here I write, so we put x is equal to 2. What about the numerator comes? Numerator, we put x square. So 4 minus 3 into 2, 6 plus 2 divided by, what about the denominator? 2 minus 2. So what do you get? 4 plus 2, 6, 6 minus 6, 0 divided by 0. So we can get indeterminate form. So if you apply directly, we can get indeterminate form. So we do something. So we can write the given problem. We can rewrite. That is, we factorize. So x square minus 3x plus 2. How will you factorize? X minus 1 into x minus 2. I think we know, we are familiar to factorize in the quadratic equation. So quadratic factor we can easily factorize. So this can be factor like this, x minus 1 into x minus 2 and denominator x minus 2. So x minus 2 cancel, we can get x minus 1. So now the function can be simplified into x minus 1. So hence limit extend to 2, the given function is equal to limit extend to 2 x minus 1. Now we put x is equivalent to 2, 2 minus 1, 1. So the value should be 1. Fourth problem, evaluate limit extend to 1 x power 4 minus 1 by x cube minus 1 if it exists. So now here also the same case, if we put x is equal to 1 directly, 1 power 4 minus 1 divided by 1 cube minus 1. So we can get indeterminate form. So in that case, we can factorize in the numerator x power 4 minus 1. So x power 4 minus 1 we can write x square whole square minus 1 square. That is a square minus b square. So a plus b into a minus b. So we can write it as x square minus 1 into x square plus 1. So we have in the numerator. Denominator, a cube minus b cube. You know the formula. What the formula? A cube minus b cube. So a cube minus b cube is nothing but a minus b into a square plus ab plus b square. So using this formula, the denominator x cube minus 1 can be written as x minus 1 into x square plus x plus 1. And further in the next step, so again x square minus 1 using a square minus b square. So we can get x plus 1 into x minus 1. And second term we can write as it is, divided by x minus 1 into x square plus x plus 1. X minus 1 we cancel. So we can get x plus 1 into x square plus 1 divided by x square plus x plus 1. Now we put x is equal to 1. So x is 1, 1 plus 1. Here 1 square is 1 and denominator 1 square plus 1 plus 1. So after simplifying this, we can get 4 by 3. Fifth problem, this is the easiest one. So evaluate limit x into 2, x square minus 4 divided by x minus 2. So in the same case, then directly if we apply, what you get? 4 minus 4 divided by 2 minus 2. So we can get 0 by 0, nothing but indeterminate form. So what we have to do? We try to factorize. So in the numerator, so x plus 2 into x minus 2, a square minus b square formula we can apply, and x minus 2 cancel. After cancel this, if we apply x is equal to 2, so 2 plus 2, 4. Sixth problem, in the same case, evaluate limit x into 2, x cube minus 8 divided by x minus 2. So that 8 can be written as 2 cube. So we can apply a cube minus b cube formula again here. So a minus b into a square plus b square a minus b into a square plus ab plus b square. So using that formula, we can have x minus 2 into x square plus 2x plus 4. The denominator we can write as it is. Now we cancel x minus 2, x minus 2. We can get x square plus 2x plus 4. And now we put x is equal to 2. We put x square is 4 plus we put x is equal to 2, 2 into 2, 4 and 4. So after simplify this, we can get 12. So we make a note that previous all the problems limit extend to a finite value. But what about now? Limit extend to infinity. So evaluate this problem. Limit extend to infinity. X square plus x square, x cube plus x square plus x plus 1 divided by x cube plus 3x square plus 5x plus 2. So now we put x is equal to infinity directly. What will happen? Infinity divided by infinity. So again we can get indeterminate form. So here we cannot factorize. The idea is if we have x is equal to infinity, in the numerator the highest power of x we can take outside. Similarly in the denominator also we can take outside. So here the highest power is nothing but x cube. So x cube we can take outside in the numerator. So what we get? 1 plus here 1 by x plus 1 by x square plus 1 by x cube. Similarly here x cube we can take outside. So we take x cube outside. What you get? 1 plus 3 by x plus 5 by x square plus 2 by x cube. Now that x cube we cancel and we have. Now we put x is equivalent to infinity. So we substitute x is equal to infinity. What you get? Here anything by infinity 0. So this term are all become 0. So 1 by 1. So these are all 0. We can get 1 by 1. So the final answer is 1. So the general idea is if we have limit extend to infinity, if we have algebraic functions, we try to take the highest power of x outside in the numerator as well as in the denominator and try to cancel. After that, we can apply the limit. And now we look at this problem. Evaluate limit extend to infinity, root of x square plus 1 minus root of x square minus 1. So here the new thing is in the problem we have square root. So here also if we apply extend to infinity, so then problem become infinity, infinity minus infinity. So what we are going to do, the problem we can rewrite. So take the function root of x square plus 1 minus root of x square minus 1, and here we can multiply and divide by a factor. That factor is nothing but here we can take the plus, that is x square plus 1 plus x square minus 1 divided by square root of x square plus 1 plus root of x square minus 1. The idea is we try to remove the square root in the numerator. So now this is become a minus b into a plus b. So we can have a square minus b square. So the first term square minus second term square. The new denominator we can write as it is. Now that square and the square root will cancel. So we can get x square plus 1 minus x square minus 1. So after simplifying this, what you get, x square minus x square cancel, 1 minus minus plus 1. So 1 plus 1, 2. In the numerator we have 2 and denominator we can write as it is. Now we put x is equivalent to infinity. So what you get here, this term is nothing but infinity and this term is nothing but infinity, that is 2 divided by infinity. So anything by infinity, what is the value? Anything by infinity is nothing but 0. So the value of this limit is nothing but 0. While applying the limit, so we have an important rule. So finding limits using L'Hopital rule. So L'Hopital's rule can only be applied in the case where direct substitution gives an indeterminate form. So already we had seen some of the indeterminate form. So mainly we have 7 indeterminate form. They are 0 by 0, infinity by infinity, infinity minus infinity, 0 into infinity, 1 power infinity, 0 power infinity, and infinity power 0. So these are all indeterminate form. So in that case, we need to do is differentiate the numerator and the denominator, numerator and differentiate the denominator and then take the limit. That is, we can differentiate the numerator independently and also we differentiate the denominator independently with respect to that variable x, and then again we can apply the limits. Now we see the problem, ninth problem. Evaluate limit x tend to 0 sin x by x. So the function is nothing but sin x by x. So if you put x is equivalent to 0 directly, sin 0 by 0, sin 0 value is 0. So 0 by 0 we can get indeterminate form. So by applying L'Hopital rule, we get, that is, we differentiate the numerator independently and also differentiate the denominator independently. So differentiation of sin x is nothing but cos x and the x is nothing but 1. Now we put x tend to 0, x equal to 0, cos 0 is 1, cos 0 is 1, so 1 by 1 nothing but 1. We'll see one more example. Evaluate limit x tend to infinity e power x by x square. So solution, limit x tend to infinity e power x by x square is equivalent to, we put x is equal to infinity, e power infinity by infinity. E power infinity is nothing but infinity. So infinity by infinity we can get indeterminate form. So by applying the L'Hopital rule, we differentiate the numerator independently and the denominator. So differentiation of e power x is nothing but only e power x and denominator x square is nothing but 2x. Now we apply x tend to infinity. So we can get e power infinity by infinity, that is e power infinity is infinity and denominator already infinity. So we can get indeterminate form. So what we are going to do now, again we can apply the L'Hopital rule, that is we differentiate numerator independently and denominator independently. So e power x differentiation is nothing but e power x, denominator 2x, we differentiate we can get 2. So now we can put x tend to infinity, that is e power infinity by 2, e power infinity is infinity. So the value is nothing but infinity. One more problem we will see. Evaluate limit t tend to 0 square root of t square plus 9 minus 3 divided by t square. So we had discussed one problem. In the numerator, if we have square root, we try to eliminate that square root and then try to apply the limit. So the same idea we are going to do here also. So limit t tend to 0, square root of t square plus 9 minus 3 divided by t square. So here we multiply and divided by a factor that is nothing but square root of t square plus 9 plus 3. So this term we multiply and divide. And denominator we can get t square into square root of t square plus 9 plus 3. But numerator we can write using the formula. We try to simplify a minus b into a plus b. So a square minus b square. So square root will cancel. We can get t square plus 9 and minus b square. B is 3. So 9 by t square. And this factor denominator we have the same. So now that 9 cancel and t square cancel, we can get only this term. So now in this we put t is equivalent to 0. What do you get? 1 by square root of 0 plus 9 plus 3. So 9 is nothing but root 9 is nothing but 3. So 1 by 3 plus 3 we can get 6. So we have 1 by 6. Next problem. Prove that limit x tend to 0 mod x divided by x does not exist. So already we had seen earlier what is mod x, absolute function. So mod x can be defined like this. If x is negative, mod x is nothing but minus x. If x is positive, mod x is nothing but plus x. For x is positive, mod x is plus x. Therefore, limit x tend to 0 plus mod x by x. Mod x is nothing but x. So x cancel, we can get 1. For x is negative, x is less than 0, mod x is nothing but minus x. So limit x tend to 0 minus mod x by x. So mod x is nothing but minus x. So we can get minus 1. Left hand limit and right hand limit both are not equal. Therefore, we can say limit does not exist. So now we have a question, why we need to find out left hand limit and right hand limit? The answer is the function is defined, distributed into broken interval, that is less than 0 and greater than 0. So we need to find out limit value at x tend to 0. Here x tend to 0. Left hand side we have different function, right hand side we have different function. Therefore, in that case, we can find out left hand limit and also right hand limit. If both are equal, then we can say limit exists. If both are not equal, then we can say limit does not exist at the particular point. That's why we are find out left hand limit and right hand limit here. So 13th problem. So consider this, if f of x is equal to root of x minus 4 if x is greater than 4, 8 minus 2x if x is less than 4. So determine whether limit x tend to 4 f of x exists. So here we look at this, the point is 4. So we need to evaluate limit x tend to 4 f of x. So less than 4 we have a different function, and above 4 greater than 4 we have a different function. So x is less than 4, what we have 8 minus 2x, but above what we have above 4 we have x minus 4. So we need to find out limit at x tend to 4, that is the point. So in this case we have to find out left hand limit and right hand limit. So x tend to 4 in the left hand limit and also right. So limit x tend to 4 plus right hand limit we are finding. In the right hand side, what is the function? Root of x minus 4. Now we put x is equal to 4 here. 4 minus 4 we can get 0. Similarly, in the left hand side, limit x tend to 4 minus f of x. So limit x tend to 4 minus, what about the left hand side function? 8 minus 2x. Now we put x is equal to 4 into 2 8. So 8 minus 8 we can get 0. So now we observe this, left hand limit and the right hand limit both are exist and equal to 0. Therefore limit exists and limit x tend to 4 f of x is nothing but 0. One more problem we will see. Limit extend to 1 f of x exists for the function f of x. F of x is given like this: x square plus 1 if x less than 1. If x is greater than or equal to 1, x minus 2 whole square. So in the same case, so take the point 1. So if x is less than 1, left hand side, what is the function? X square plus 1. What about right hand side? Above 1, x minus 2 whole square. So we need to find out limit value at x tend to 1. So this is the midpoint. So left hand limit we need to find out, and also right hand limit we need to find out. So left hand limit extend to 1 minus f of x. Left hand side, what is the function? X square plus 1. So we put x is equal to 1 now. 1 square is 1, 1 plus 1, 2. So left hand limit value is 2. Similarly, for right hand side, limit extend to 1 plus. So limit extend to 1 plus. What about right hand side function? X minus 2 whole square. Now we put x is equal to 1, 1 minus 2 whole square. So minus 1 whole square is nothing but plus 1. Now we observe this: left hand limit value is 2 and the right hand side limit value is 1. So 2 not is equivalent to 1. So limit at the particular point 1 does not exist. Now we will see important theorem, namely we call it as skews theorem or sandwich theorem. So it theorem says that if f of x less than or equal to g of x less than or equal to h of x, we consider three functions f, g, h, and we have a condition f of x less than or equal to g of x less than or equal to h of x when x near a, and limit extend to a f of x is equivalent to limit extend to a h of x is equal to capital L. Then limit extend to a g of x is equivalent to L. That is, the limits are exist f of x and g of x as the limit and equal to common value L. So f of x as limit, that is equal to L, and h of x as the limit is equivalent to L. Then this theorem says that for g of x limit exists and the limit value is nothing but the same L. So based on that, we have a problem. Show that limit extend to 0, x square into sine of 1 by x is equivalent to 0. We need to prove the limit value is nothing but 0. Now we can take g of x is equal to the whole function x square into sine of 1 by x. So now if we apply limit extend to 0, sine of 1 by x, what you get? The value does not exist. So that is, we put x is equal to 0, 1 by 0 infinity, sine infinity. So value does not exist. So we cannot use the product limit concept. That is, limit extend to 0, x square sine 1 by x. We put what you get here, we put x equal to 0 here and here infinity. So we can get indeterminate form. So we cannot apply. So now we can use this sandwich theorem. That is, we know trigonometric function sine 1 by x always lies between minus 1 and plus 1. So consider this. Now we can multiply x square on both sides. So what you get? Minus x square less than or equal to x square into sine of 1 by x less than or equal to x square. So now we can see, take this is the function and this function. So limit extend to 0, x square, what do you get? We put x equal to 0, we can get 0. So this value, if we apply the limit, we can get 0. Similarly, in the left hand side, limit extend to 0 minus x square, that is also 0. So this function as limit is equal to 0, and this function is also have limit into 0, equal to 0. So by applying that sandwich theorem, this one is also has limit at the particular point and exist and is equal to 0. Thank you for watching this video. Please like, share and subscribe. Thank you.